Hey everybody, welcome back to chemistry. And so what I want to do now is talk about something called the first law of thermodynamics. And so what that is really just a very careful quantification of the law of conservation of energy. So to introduce this, I want to remind you of sort of an example I gave maybe a couple of play posits ago where you were at a campground and we had a situation where there was a before and there was an after a process. And the process that was going on at the campground was you were burning logs at the campfire. And so let me talk a little bit about that. So here are the logs. And we said that the logs are the system. And then everything outside of the logs are the surroundings. So before you burn the logs, the system had quite a bit of internal energy. But then you burn the logs, so here's a flame over the logs, and so you burn them and you went from the before situation to the after situation. And so the after situation is the system now is just ashes. So the system is still there, but now it's really quite reduced in size, and it's ashes. Also importantly is the energy of the system was quite a bit less than it was before. Ashes just don't nearly have as much energy as logs. And so what we talked about was during this process, what was going on is that you had energy that was leaving the system and going into the surroundings in two forms. One form was the form of heat, and the other form was that of work. And so what I kind of pointed out was here the law of conservation of energy was met because the law of conservation of energy states that you must have as much energy after a process as you had before the process. Another way you could state the law is by saying that any energy lost by the system must be gained by the surroundings. And we saw that here in this case, in that, as I recall, the system lost a total of 495 kilocalories of energy, and this was lost to the surroundings, and it was in the form of heat and work. So now what I want to do is talk a little bit about this in more detail and assign some variables that you haven't seen before, and then this will bring us to an equation, which is the first law of thermodynamics. So I'm going to talk about the logs again. We're going to start up here again, but I'm just going to talk about them a little bit more. So here are the logs. See if I can find a good pen here. There we go. Okay, so we have 4 logs here. As I recall, we were dealing with 4 logs. And so this is before burning. And so here these logs, again, are the system. And so as I recall, I said last time that the logs have a great deal of internal energy. And so the internal energy is in mostly the form of chemical energy. And also there's a little bit of thermal energy. And so here I think we just totally counted, say, the energy to be, for example, 500 kilocalories. Okay, so now what I want to do is I've said that these logs have 500 kilocalories of energy. So I want to say that this is a variable. The variable is called internal energy, which has the symbol capital U. So here we have internal energy capital U. So now this is sort of before we burn the logs. So if we wanted to, we can break it down a little bit further and say, well, this is the initial value of U. So again, U is the internal energy within the system. The system is the logs, and the logs again will have mostly chemical energy and a little bit of thermal energy. Okay, so now we're going to go ahead and start this process. So we're going to set the logs on fire, and so to indicate that there's a fire here, I'm trying to draw a flame here. And so the logs are burning, and then afterwards what we have is a system, but now the system is just comprised of ashes. So here is the system here. Now, let's think about how much energy might be in the system. We would not expect much energy to be there. And the reason is that the chemical energy that the logs had has been mostly lost in the form of carbon dioxide and water and heat that was released into the surroundings, the environment. There's probably going to be a little bit of thermal energy left in these ashes. And so the total energy or internal energy of the system after the process is much lower. So U here of the ashes here is going to be, say, 5 kcals of energy. And so now we can call this U final. Okay. Now, what you can see is what the internal energy before was much greater than the internal energy after. And we know why is because that when we burned these logs, all this internal energy was released into the environment, which is the surroundings. So I'm going to write surroundings here. And so any internal energy lost by the system, and it looks like we lost 495 kilocalories, has been picked up by the surroundings. Now let's talk about the forms that this energy was lost in. So one of the major forms was heat. And so most of the energy in these logs has been released in the form of heat. Now the variable for heat is little q, and let's just assign this number. I think last time I assigned this to be 490 kilocalories. Okay. And now also I kind of pointed out that a little bit of work is done by the system on the surroundings. So here we have a little bit of work, and so this is work, which I'm going to symbolize by W, and this is about 5 calories or kilocalories. Okay, so you might be wondering, well, how is it possible that logs can do work? And so sort of the example I'm thinking about is the popping sound you hear when you have a campfire is an indication that the system of logs in your campfire is doing work. So let me explain that. So the popping sound you hear is that you have the logs and they have liquid inside them, say water, and the water will get very hot and then it will boil within the logs. Now, the interesting thing is that the volume of the gas is about 800 times the volume of the liquid. And so when you boil water within the logs, you're going to have that liquid boiled off to 800 times the volume in gas. And so that's going to be a lot of pressure that's going to be put on in the inside of the log, and it'll burst the log and you'll hear a popping sound. So what is going on is the system is creating volume that is working on a constant pressure. So the system is really doing some work on the surroundings, and so the system is losing a little bit of energy in this fashion, and we'll call it 5 kilocalories of energy. Okay, so with this simple model, what I want to do is give you the equation for the first law of thermodynamics, and I'll break it down a little bit. Okay, so the first thing I want to do is evaluate the change of energy of the system. So we have delta U, which is the change of internal energy of the system. How would you calculate that? So it's calculated in a certain way in that you always take the final amount of internal energy and subtract from it the initial amount of internal energy. And so let's go ahead and do that calculation. So the final value is 5 kilocalories. I'll leave out units. The initial value is 500 kilocalories. And what we get is when we have 5 minus 500, we get negative 495 kilocalories. Okay. So as I was pointing out here, any internal energy lost by the system must be completely accounted for by the amount of heat and work that was lost by it. And so that is described with a simple equation called the first law of thermodynamics. So I'm going to give you that equation. So the first law of thermodynamics is this equation. It's going to be the change of internal energy of the system here, which was our logs, must be equal to any changes of heat that occurred in this process plus any changes of work in this process. And so here, this is the first law of thermodynamics, so I'm hoping you will write this in your notebook and write first law of thermodynamics. Okay, so now we're getting into an important consideration as to what exactly the values are for these constants. So we figured out what the value of delta U is. That is correct. So the value of delta U is negative 495 kilocalories. Now let's talk about what the values of Q and W are. And so the magnitude of the heat of Q is going to be 490, so I'll write that here. And the magnitude of the work is 5. But here's the thing. We must have an equal amount on the left side of the equation versus the right side of the equation. Therefore, we have to give appropriate signs when you have a situation where heat is released by a process and when system is doing work on the surroundings as it was doing here. And so if that is the case, if you have the system that is releasing heat and work is being done by the system on the surroundings, then you must give these appropriate signs for these values. And so we have to make heat to be negative 490 and work to be negative 5. The reason we do that is now on the right side of the equation we have a total of negative 495 units of energy accounted for by heat and work, which is equivalent to the negative 495 units of energy, which is the change of energy of the system. So one of the things you can sort of see with the first law of thermodynamics is you will have changes of energy in the system, but what you have to be very careful about is making sure that your value of heat has the appropriate sign and your value of work has the appropriate sign. So now I'm going to sort of go over the computer and talk about that right now. So here we have, again, just a restatement of the first law of thermodynamics, and that the delta U, which is the change of internal energy of the system, is equal to any heat changes that are occurring in the process plus any work changes that are occurring in the process. And so there I have the variables defined. Here I'm kind of pointing out that while delta U is a state function, Q and W are not state functions, and that their values sort of depend on the exact processes that is occurring. And so these are considered to be path functions. Okay, so now just to kind of point out a little bit more detail, when you use this formula that delta U of the system is equal to Q plus W, and you're trying to figure out what the sign for Q and W are, remember this, it's always from the perspective of the system. Therefore, if the system is releasing energy, this would be an exothermic reaction like the burning of logs, it's losing energy, so the sign of Q would be negative. If the system is doing work, for example, the system includes a reaction that's producing a gas that's increasing in volume against atmospheric pressure, then the sign of W is negative. If the system is absorbing energy, in other words, the surroundings are giving energy to the system is absorbing it, that would be an endothermic reaction, then the sign of Q would be positive. And if the surroundings are doing work on the system, for example, the volume of a reaction is decreasing, then the sign for W would be positive. So let's practice figuring out what the correct signs are for these changes that I'm kind of mentioning here. So what we'll have to do is figure out, are we describing a situation where the system is losing or gaining heat, which is symbolized by Q, or is the system doing work on the surroundings, or the surroundings doing work on the system? So we have to sort of figure these out. Okay, so the first one is this. What is the symbol and sign for a reaction that is exothermic? Okay, so that one shouldn't be too hard. And so if a reaction is exothermic, that means the system, which is the chemical reaction, is losing energy into the surroundings. And so if that is the case, if the system is losing energy into the surroundings, we're talking about heat as being lost into the surroundings. And if the system is losing the energy into the surroundings, then the sign of Q, which is heat, should be negative. Okay, what is the symbol and sign for an ice cube melting and cooling the surrounding beverage? So now let's pretend that the ice cube in the beverage itself is the system. So let's think about what's going on here. If an ice cube is in a beverage and it's melting, what must be happening is that you must have energy leaving the beverage and going into the ice cube, which is the system. So that is heat leaving the beverage and going into the ice cube. And so the system is gaining energy from the heat. And so if that's the case, it should be a Q here we're talking about, and it's going to be positive because the system here has more energy after this change than before the change. Okay, what is the symbol and sign for a metal cylinder being rolled up on a ramp? Okay, so imagine like you're trying to push some heavy like 55-gallon drum up a ramp. So what you'll know is you're going to be doing work on the 55-gallon drum. And so if that is the case, if you were the system, then because you're doing work on the surroundings, which is the drum, then you would have a negative W. But here we're pretending that this 55-gallon drum itself is the system. So what the drum is doing, it's receiving your work. So if your work is negative W, then if it turns out that the drum is the system, is receiving work from you, the system, the drum, must be positive W. So the next one is, what is the symbol and sign for steam condensing on skin causing a burn? Okay, so let's think about what condensing steam is. And so you're taking steam, which is water basically in the gaseous state, and so it's probably going to have a very high amount of energy. And so what it's doing is condensing on your skin, and it's going to the liquid state, which is going to have less energy. And so if the system here is the condensing steam, basically it must lose energy to go from the gaseous state to the liquid state. And so if it's losing energy, that means it's an exothermic reaction, so it should be negative Q. Okay, what is the symbol and sign for a gasoline mixture exploding in an engine cylinder and pushing the piston in the cylinder down? Okay, so here we're going to have some kind of Q term for heat and work term for W. So let's figure out which sign values are for each of these. So imagine that you have a car cylinder, and then let's say the piston is up in the cylinder, and then you just injected gasoline on top of the piston, and you ignite the gasoline and it explodes. And when it does, it releases carbon dioxide, water, and energy. So it's releasing energy into the surroundings. And so that would be an exothermic reaction. So that would be a negative Q. On the other hand, let's talk about what's going on with work. So you have a chemical reaction, the gasoline exploding, that is doing work on the piston. And so if that's the case, you have the gasoline doing work on the piston, which is the surroundings, and so W should be negative. So we have some more examples here. What is the symbol and sign for a reaction which is as follows? Okay, so this is a little bit trickier. So here you have to sort of make a judgment of the sign of work by noticing the relative number of moles of gas there are on the reactant side of the reaction versus the product side of the reaction. So let me talk a little bit about that with this example. So if you look at the reactant side of this reaction, we have magnesium reacting with hydrochloric acid. And so one thing that you can see is that the states of the magnesium and hydrochloric acid, they're not in a gaseous state. On the other hand, when that goes to products, you produce magnesium chloride and hydrogen gas. And what you can see is that one of the products, hydrogen gas, is in a gaseous state. And so we're wondering, is there any kind of work associated when you have this chemical reaction going from reactants to products? Well, basically, you have a bunch of reactants that are producing a gas. So imagine the gas is sort of billowing out of the reaction, and it's pushing its volume out, and it's pushing it out against atmospheric pressure. And so if that's the case, then the system, which is the chemical reaction, is doing work on the surroundings. And so if that's the case, then the term for W should be negative. Okay, let's look at this one. So what is the symbol and sign for a reaction, the system, which is as follows? So here we have hydrochloric acid reacting with sodium hydroxide, and we're producing water and HCl. Now, none of the reactants or products are gases, so we don't have to worry about an evaluation of work based on that. But we do have an energy term in the chemical reaction. You can see it's on the right side, it's on the product side. And so if that's the case, this is an exothermic reaction, so we're probably referring to a negative Q. Okay, what is the symbol and sign for a reaction which is as follows? And so here we have a situation where the reactants, whether you have A or B, are both in a gaseous state. And the products, whether you have C or D, are both in the gaseous state. And so what we have to sort of figure out is, do the reactants have more volume or do the products have more volume? And so the way you evaluate that is you work with the assumption that equal moles of different gases have equal volumes. So for example, you can see that in this chemical reaction that 4 moles of A reacts with 2 moles of B and produces 1 mole of C and 2 moles of D. So because of what I just said, you can also say for this problem that 4 liters of A will react with 2 liters of B to produce 1 liter of C and 2 liters of D. And so what you can sort of see now is you can sort of compare the volume of the reactants versus the volume of the products. And so we can assume, for example, these numbers also refer to liters. And so on the reactant side, what you can see is you have 6 liters of gas. On the product side, you have 3 liters of gas. What this is going to be is this is actually going to be work done from the surroundings on the system. And the reason is because you kind of know that, for example, let's say you were in a situation where your products had more volume than the reactants. If that was the case, then work would be negative because you're doing work on the surroundings. But here we have sort of the opposite case. Here, the reactants have more volume than the products. What is going on? It must be that during this chemical reaction that the surroundings are sort of doing work on this chemical reaction. And so the chemical reaction is a system, so it must be plus W. Okay, here's another example of this kind of situation. Now notice that here we only have to be concerned with A and C because B is not a gas. So we have 2 liters of A reacting with B to give us 4 liters of C. And so what you can see as you go from reactants to products, that the volume of the system is expanding quite a bit. And so if that's the case, then you have the system doing work on the surroundings, and so it should be that W is negative. Okay, what is the sign and symbol when you take a piece of wire and bend it back and forth? Okay, if you do that, basically what are you doing? You are doing work on the wire, and if the wire is the system, I assume it is, it's receiving the work, so it should be positive W. Okay, so let's move on. So practice first law problems. I have some more problems here, and so what I would do is I would encourage you to go over these on your own and sort of understand why the answers are what they are. So we'll move on from that.